So we just saw how we can use prefixes and add them to our units to shorten our numbers. We can also use scientific notation to do the exact same thing. So there's two parts to scientific notation. There's a decimal part and an exponential part. So the exponent represents if we have a very large number or very small number. So if the exponent is positive, we have a very large number. If the exponent is negative, then we have a very small number. So I'm going to show you here how to put a number into scientific notation. Okay, so we have 702,000. So if I don't want to work with that large of number, I can use scientific notation. Okay, so let me show you here. Let me get this. Okay. 702,000. Okay, so we don't have a decimal here, but we imagine that there's the decimal's right here, right? But when I write scientific notation, I want it to be to the right of our first number, or first non-zero number, okay, which is 7. So I want it to be to the right of my 7. So I'm going to move my imaginary decimal 1, 2, 3, 4, 5 spots, okay? So that 5 tells me what my exponent's going to be, okay? But before I do that, I'm going to rewrite the number with the decimal right there, 02. Okay, I'm going to leave off these zeros and just write the 02, and I'm going to explain here in a minute that those zeros are not significant. So we'll get to that here in just a minute. So I'm just going to write 7.02. Okay, so that's the decimal portion, but I can't just leave it 7.02 because that does not represent 702,000. So I've got to add the exponent portion, so times 10. And I moved it 5 places, and I moved it to the left, so the exponent is going to be positive 5. So if I move the decimal to the left, I'll have positive exponent, which means I have a very large number. But if I move the decimal to the right, then I'm going to have a negative exponent, which means I have a very small number. Okay, so just showing you the powers of 10 here. So if I have 10 to the 1, that means I have a 10, 10 to the second times 100, 10 to the third is 1,000, and then going the opposite direction, 10 to the negative 1 is 0.1, 10 to the negative 2, 0.01, 10 to the negative 3, 0.001, okay? So you don't have to remember that. Again, you can just move those imaginary decimals to get the correct scientific notation. So I want to show you some more examples here. Okay, so if I have 0.00, see here, I have 5. What happened? There we go. 4, 5. Okay, those are our zeros. 6, 8, 2, 4, 0. Okay, so I don't have to imagine my decimal in this one. I can see it right here, right? So I want to move it to the right of my first non-zero digit, which is 6. So I'm going to move it 1, 2, 3, 4, 5, 6 places. Okay, so I'm going to rewrite my number. I'm going to get rid of all these zeros here because, again, we're going to look in a minute to see that they're not significant. I'm going to 6.8240. Okay, this 0 is significant, so I'm going to keep it. Okay, now I have my decimal portion. I need to add my exponent. So we moved it to the right 6 spots. So since I moved it to the right, it's going to be a negative 6. So again, that negative shows me I have a very small number. Okay, we'll do one more example here. 250,000. Okay, so I have an imaginary decimal right there. 1, 2, 3, 4, 5. I'm going to rewrite 2.5. Okay, I'm going to leave off all these zeros. And I'm going to write my, so that's my decimal proportion. I'm going to write my exponent. I moved up 5 spaces to the left, so I'm going to have a positive exponent. So again, this is just a way to shorten your number, not have to deal with all those zeros. And again, I'm going to go over what makes a number significant, what doesn't. But in scientific notation, I do want you to remember this. In scientific notation, it only shows the numbers that are significant. So I'm going to write this down. Numbers that are significant. I'm running out of room. There we go. So it only has numbers that are significant in scientific notation. So anything that's insignificant, we leave out. Okay, so going back to units, we know, we're using SI units and measurements. So for length units, the SI unit is meter. For mass, it's kilogram, and energy, the SI unit is joule. So we talk about this because we're going to look at temperature. So energy is just the capacity to do work and transfer heat. Okay, so that's the big thing, is that heat transfer. So we're going to be looking at temperature. This temperature measures how hot or cold a substance is. We have 3 different scales for temperature. We have Fahrenheit, which is what we're used to, right? If you wake up and see that it's going to be, 98 degrees that day, we know that that's in Fahrenheit, okay? Celsius is normally what we use to measure temperature in the lab. And then Kelvin is something you're probably not real familiar with, but Kelvin is also a temperature scale. Okay, so we can see the 3 different scales here in the picture and kind of get an idea of how they're different. So at the bottom it says water freezes, and we know that water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and water freezes at 273.15 Kelvin. Okay, so now that's all the same, but the different temperature scales show the different numbers, so you can kind of see how they relate. And then at the top, water boils at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin. So there's no degrees in Kelvin. Okay, so absolute 0 is 0 Kelvin. That's the absolute lowest temperature you can get, is 0 Kelvin. There is no molecular motion past 0 Kelvin, okay? So Kelvin is all about molecular motion. We'll get more into that when we talk about chapter 10. But for now, that's what you need to know. Okay, so to be able to go in between these temperatures, we use these equations right here. So I do want you to know these equations. So in the first one, if we're looking for Fahrenheit, we have to use degrees Celsius. So we plug in degrees Celsius, we multiply that by 1.8 and add 32. So the way I remember this, because you're using the same numbers, 1.8 and 32. The way I remember this is degrees Celsius, the number is always lower than degrees Fahrenheit. So we've got to multiply and add. Okay. Then Celsius, if we are looking for degrees Celsius, we have to plug in degrees Fahrenheit, and we're going to subtract and divide because degrees Fahrenheit is always bigger. So we've got to subtract and divide to get to degrees Celsius. So again, that's just kind of how I remember it. And then Kelvin, we have to have degrees Celsius, and we add 273 to get Kelvin. So there's no equation to go straight from Fahrenheit to Kelvin. We have to go through degrees Celsius on that. So let's use these equations. In the first one, we're going from degrees Celsius to degrees Fahrenheit. So I'm going to use this equation, and we're going to get 1.8 times 54. Remember, degrees Fahrenheit is always bigger, so we're going to multiply and add here. So we're going to add 32, and that gives us 129 degrees Fahrenheit. So there's our first one. Second one, we're going from 98 degrees Fahrenheit to Kelvin. So we know we don't have an equation to get us there, so we're going to first solve for degrees Celsius, and then we'll solve for Kelvin. So degrees Celsius, we're going to subtract and divide. So 98 minus 32 divided by 1.8. And gives us 37 degrees Celsius. And then all we have to do is plug that in here. 37 plus 273 gives us 310 Kelvin. Okay. And then last one, we have 205 Kelvin. We want to know what that is in degrees Celsius. So we know that Kelvin is equal to degrees Celsius plus 273, right? That's the equation. So if I want to solve for just degrees Celsius, right here, I just have to get that by itself. So I'm going to move 273 over here and subtract, right? So it becomes 205 Kelvin minus 273 equals negative 68 degrees Celsius. Okay, so these equations aren't bad. That you just, don't. The hardest thing I think is, not getting them mixed up. Okay, so you do need to have these memorized. Be sure and practice these